All right, so here we have another problem that's similar to problems that we've seen before in terms of using Newton's laws of motion. So in this case, they're asking us to use the concept of work and energy to find the speed of the blocks, the system of blocks that are connected by a cord right before the hanging block strikes the ground. And so we're going to start off by considering part A, where there is no friction on the table. So for this part right here, there's no friction. So I'm just going to kind of cross that one off in our picture. And then we're going to consider what happens when there actually is friction. So they do give us the mass of each of these objects. So the mass on top is 2 kilograms, the hanging mass is 1 kilogram, and then the height above the floor is 0. So we're going to use the concept of work energy, and because it says that the table is frictionless, we can assume that energy is conserved. So that means that the energy initial of the system is equal to the energy final of the system. All right, so we do have a system of blocks. When they are moving, once they start moving, they are going to always have the same speed at the same time, like that. So just before the hanging mass hits the floor, it will have some final speed. Actually, let's do this. Let's erase those. And let's just say, like, right before it hits the ground here, it's going to have some final speed, and this one will be moving at some final speed over here. All right, so what do we know about the motion? Well, the first thing that we realize is that they do start from rest. They haven't told us otherwise, so we're going to assume that they start from rest. And in terms of the mass that's on the table, the height that it's at is always constant. So its initial position vertically is the same as the final position vertically. I'm calling it h, but we certainly could also say, we could write it this way, in terms of its position, vertical position, right? So in my picture, if I choose the lowest point as my 0 position, what we're saying here is that this height for the mass is always the same, which means that its gravitational potential energy is never going to change. We also know that the initial position of the hanging mass is some height above the ground. So this would be y initial for the hanging mass is just some height h, and its final position is going to be 0. So I can now apply energy conservation, and I need to consider the fact that energy is a combination of kinetic energy and potential energy. So I'm actually going to write it down a little further here so I have some more space. So the initial energy of the system would be the combined masses, and they may be moving with some initial speed. So they could have kinetic energy. And then individually, each one of these could have some gravitational potential energy. And then as the mass falls, they both could have kinetic energy. And I'm just putting it as a combined system because they have the same speed at any given time. And then each one could have some final gravitational potential energy. And I am running out of space. There we go. All right, well, a lot of these terms are going to cancel. So the initial speed of the masses are both 0. They start from rest. So those are 0. And then the gravitational potential energy of the mass that's on the table doesn't change. So these two terms are going to cancel out because it's always at the same height. And then finally, the final position of the hanging mass is also going to be just before it hits the ground. So we know that this is equal to 0. So we have a situation where the gravitational potential energy of the hanging mass, which is this term right here, gravitational potential energy of the hanging mass, as it falls, it converts that energy into kinetic energy of the system. So I have mg, the hanging mass, times gravity, times the height that it is to start with, has to equal 1/2 the total mass of the system times that speed squared, because they're moving together. So now I can put my values in. So the hanging mass is 1 kilogram, gravity is 9.8. The height is 2 meters above the ground, and that has to equal 1/2 the combined mass. So 1 kilogram plus 2 kilograms is 3 kilograms times V final squared. So I have a little bit of algebra here. So this side is 19.6. This is 1.5 kilograms. Can divide both sides by 1.5. I get 13.07 meters squared seconds squared equals the final speed squared. And then I would take the square root of both sides, and I get that the final speed is 3.61 meters per second. All right. So we know how fast both objects are moving after the mass falls. There we go. Like that. There's another part to this question. There's a part C that asks, can you find the tension in the rope for either of these cases? So in order to find the tension in the rope, you have to look at a single mass, similar to what we would have to do if we were applying Newton's laws of motion. So energy is still conserved in the system. We just have to redefine our system. So I am going to erase some of this, perhaps. There we go. Whoa, okay, that's all right. It erased everything. There we go. Okay. So we're going to start again, and we're going to consider just one of these masses as our system. And we can choose any of the masses that we want. And I think I said energy is conserved, but if we look at a single mass, energy is no longer conserved because the tension is actually doing work on the system. So we're going to call our system to be the big mass here. And then if that's the mass that we're looking at, the tension here is going to do work on the system. So we know that the net work done by non-conservative forces is equal to the change in energy, kinetic energy plus potential energy final minus kinetic energy initial plus potential energy initial. So this is just work done by non-conservative forces is equal to the final energy minus the initial energy. All right, so if we look at the work that's done by non-conservative forces, and we write this out, the kinetic energy final, this is just the large mass, so it would be the kinetic energy of the large mass plus the potential energy of the large mass minus the kinetic energy initial, or of the mass, plus the potential energy initial. So again, just focusing on the larger mass. So as we said before, the potential energy of the large mass does not change. So those two values would cancel out. And the other thing we know is that the initial velocity of the system is 0, so the initial kinetic energy of the large mass is 0. So the work done by non-conservative forces on the mass that's on the table is just equal to the final kinetic energy of that mass. So basically the tension there is pulling the mass, it's doing work, and it's causing the kinetic energy of that mass to change. So we know that the tension is a constant force, and the work done by a constant force is just the force times the displacement times cosine of the angle. So our force here that's doing work is tension. There's some displacement and then cosine of the angle. And that has to equal 1/2 the mass of the block on the table times its final speed squared. Now, in our case, the tension is acting in the direction of the motion, so the angle is going to be 0, and the distance covered for this mass up here is just the same distance that the mass down below falls. So the delta R here is going to be 2 meters. It's going to move to the right 2 meters as the hanging mass falls 2 meters. So this is going to be 2 meters cosine of 0 degrees because the tension is acting in the same direction as the displacement. And then the mass of the big block that's on the table is 2 kilograms. And we know how fast it's moving after the smaller mass, after they move, essentially, the 2 meters is 3.61 meters per second squared. So this is just T times 2 meters. Cosine of 0 is 1. And this is 13.03 joules. Divide by 2, and I get the tension is 6.52 newtons. So we have figured out how fast the blocks are moving and what the tension is using the concept of work and energy.